All right, everybody has their books? No?
We got rid of those.
All right, well, it's a pleasure to introduce Jeff Lynn, who was a NIST fellow at the NIST Center for Neutron Research. He recently retired, but he had actually, let's just say, going back even further, before that, he was faculty here way back when. He has been giving lectures at our school, I think, since the inception. So, and as you know, he's a neutron scattering expert, so take it.
Okay, thanks very much. I'd like to thank the organizers in particular for inviting me to give this talk. Everybody can hear me, okay? Anyway, and particularly Nick and Ephraim and JP would like to thank you for organizing this secret symposium on satellite. Oh, it's on. No, you didn't turn it on? Sorry. You had it on. I thought I turned it on. There you go. Right now? Now it's going to be too loud. Okay, how's that? Still too loud.
Sounds so weird to say that. All right, just...
I'll speak softly.
No, you're good.
Okay. Yeah. Now it's not. There we go. Okay, so the outline here is going to be go through the scattering basics, everything you always wanted to know about scattering in general, cross sections, form factors, X-rays versus neutrons, and then I'm going to talk about reflectometry, which is for thin films and multi-layers, particularly structural and magnetic depth profiles that you get out of that technique. Powder diffraction, one of the first things that typically you want to do for crystal and magnetic diffraction, so you can do profile refinements. Here, the subtraction technique, I'll show you how to separate out structural scattering from magnetic scattering. Single crystal diffraction, if you have a single crystal, typically you can get much higher quality data after you do the powder diffraction. Small angle scattering techniques for looking at nanoparticles, vortex lattice and superconductors, ferromagnetic superconductors, and skyrmions. Professor Chen mentioned the skyrmions today. Actually, skyrmions were discovered by the small angle scattering technique. And then dynamics, okay, and for phonons, magnons, excitations and altered magnets, the spin ice, spin liquids, things like that. And then at the end, I have some reference material. Okay, so neutron scattering, or any kind of scattering. The idea is you bring some particles in on your sample, they scatter off, and you ask how many end up in your detector. Okay, and if you want to be efficient, you'd like to have lots of detectors, but cross-section is how many in, how many end up in your detector. And this is a scattering angle. If the detector has energy analysis capability, then you can ask, looking for dynamics in addition to static structures. One of the problems is you have to conserve momentum and energy. That's the law. And in these laws, you can't break them. And I'm sure everybody's seen that, that you have a plane coming in, a plane wave coming out here, and you get a phase difference. If the phase difference is exactly one wavelength, then you get coherent constructive interference. So we start out with a periodic array of atoms, and you have, for example, d-spacing there, and all scattering is done in reciprocal space. So you take that d value, you take a plane of atoms, and you imagine that you have one wavelength of momentum transfer between those two, and that gives you one peak here. If you have two wavelengths going through there, up and down, then that's the 200. So you get a whole series here, depending on how many wavelengths you fit into that. And that's inverted, so it's reciprocal space, so it's 2 pi over d. And this is obviously 2 dimensions, but you can imagine that in 3 dimensions as well. And then there are lots of other planes. So lots of other planes give you, in essence, an infinite number of Bragg peaks where you get this coherent scattering coming in. Okay, and you have to conserve momentum and energy. Typically neutron scatterers, X-ray scatterers drop the H bar in that. And you have a change in momentum and a change in energy. So here is a reciprocal lattice point. Here's little q. Here's the total momentum transfer. Little q is the excitation. If you're looking at excitations, it's periodic in reciprocal space. So you go around any reciprocal lattice point and you measure the same excitation at the same q vector, no matter what it is. That could be magnons, could be phonons, could be electrons. Band structure, it's periodic. So that's okay. And I just threw in here so you can memorize this if you want, but neutrons, photons, and electrons, those are the dispersion relations. And nice thing, if you have a 1 angstrom neutron, you have 82 millielectron volts. This you have 12 million millielectron volts. Electrons way up there in energy. 1 millivolt corresponds to 12 Kelvin, 11.6 Kelvin. So if you're operating at room temperature, and that's where you're interested in the excitations, or lower, that's about 25 millielectron volts. And that's why neutron scattering is so useful, is that those are typically the excitations that you're interested in. And neutrons are perfectly matched to those energies, whereas photons, if you want to do inelastic scattering, you really have to work hard in order to get enough energy resolution in order to see the excitation. Okay. That'll be on the quiz later. So the 2 types of neutron sources. One is a nuclear reactor. That's the kind that you'll see tomorrow when you go out to the neutron center at NIST. You take a neutron and collide it into uranium-235. It fissions. Typically, you get about 2.5 neutrons per fission. One of those neutrons you have to use for the next uranium nucleus in order to have a chain reaction. The other 1.5 you'd like to take out and use for your instrumentation. Okay, so, and these neutrons, when they come out, there are millions of electron volts in energy. It's a nuclear process. So those energies are enormous. And you have to cool them down, and the way you cool them down is use some moderator, like we use heavy water, and the neutrons collide in with the protons, the deuterons in this case, over and over again, and you get a thermal distribution of neutrons. Our reactor basically runs at room temperature. And if you want colder neutrons, you put, for example, we have 2 different liquid helium, liquid hydrogen sources in, and that just shifts it down the low energies. And I'll show you why we want to do that. You can put hot graphite in. There are, I think, only 1 or 2 reactors that are really not necessary now with the complementary spallation neutron sources that we have. So the way a spallation source works is, instead of a neutron colliding in with uranium, you take protons and collide them in with something heavy like mercury or tungsten, and you just explode the nucleus and get a bunch of neutrons. Typically they're run as a pulse source, and so you do all the neutron scattering by time of flight. Okay, So let's, and I just threw this in so you can look at this at your leisure. Bernhard Keimer and I have a review on magnetic scattering for X-rays and neutrons, and so there's the reference. Okay, and here are the neutron cross-sections. I'm not going to go through these in detail, but the structural scattering, we call that nuclear scattering because you're scattering off the nuclei, and that's just a structure factor that will give you for elastic scattering. Magnetic scattering here gives you information about the average magnetic moment in the system, the ordered moment, the spatial distribution of the electrons, the magnetic electrons, and of course the structure and spin directions. I'm not going to go through that in general, but I do want to mention that one of the interesting things is that, yeah, this is dead.
Oh, sorry.
Yeah.
Which one?
Both of them.
Which, the big laser?
Okay. Yeah, it comes on for just a second.
Okay.
Yes. Anyway, so X-ray scattering, you scatter off the electrons. So you start at hydrogen, you got 1 electron. Unless it's ionized, then you got 0 electrons. So you can't see hydrogen with X-rays. But then as you go up the scale, you get more and more electrons scattered strongly. Neutron scattering is very different. It's a nuclear process. And so you see the big red circle there is the hydrogen scattering. Hydrogen has, turns out, one of the biggest cross sections. So hydrogen, if you're interested in biological systems, polymers, things like that, neutron scattering plays a big role in that. And then it varies between element and element because it depends on Z, the number of protons, and the number of neutrons in each element. Another nice thing is a nucleus to a one-way angstrom neutron looks like a point particle. And so that means it just scatters isotropically. All those scattering lengths are tabulated. You don't have to worry about that. So you don't have to worry about the distribution of electrons like you do in X-ray scattering. So that's one of the advantages. Okay. And now this is not working. I think this doesn't seem to be working. It's on. I can. There's another one there. Yeah, all right, sorry. Okay. Okay, so X-rays and neutron scattering. X-rays have a form factor. That's just the spatial distribution of the electrons in the system. Typically, they just use free ion calculations. And hopefully you don't have to worry about the bonding and things like that that change that distribution. If you're doing refinements with synchrotron X-ray powder diffraction, for example. Neutrons have a magnetic form factor, and that's this here. And that typically is just the magnetic electrons in the system. You Fourier transform that. Typically, those are the outermost electrons, so that typically that form factor falls off more quickly than X-rays. Okay. So for a powder, here's a powder. The way you think about a powder is you take a single crystal here and you twirl it in 2 dimensions, so you get powder rings. In 3 dimensions, those are spheres, the A-ball spheres. And then the question is, how do you measure that? Well, you put your instrumental resolution in there, and you scan through that, and you get a powder diffraction pattern. I'll show you with small angle scattering, we can actually measure the entire Debye-Shear cones. So that's a titanium gold kind of interesting system that Ethereum discovered. For glasses, amorphous materials, things like that, very similar, except you get broadened peaks. In this case, these are just resolution limited, typically. Okay. Non-perfect crystals, what about that? Well, here's a perfect crystal, and you get your D-spacing, and that gives you a delta function. So there's no, any width that you see is due to your instrumental resolution, not anything intrinsic. But what if you have a system that's correlated up to a point, and then you start to lose those correlations? So there's a correlation or coherence length that just broadens this out into a broadened peak, and that you can measure with X-rays or neutrons. Okay, and it's the width is just proportional to 1 over the correlation rate. Same thing with time. If you have an excitation, and all physicists love the one excitation that we can actually solve, harmonic oscillator, right? So this is has a period and an energy space. That's again just a delta function. But if you have width to that, a time dependence, then that gives you a width in energy space that you can also measure. So that's for imperfect crystals. This is a neutron center that you'll be there tomorrow. This is the reactor here. These are the guide halls. We started with one and we got another one. So that's why we're a national facility. When I started, it was half a dozen instruments inside the reactor. It was just what we affectionately call a mom and pop shop. And now we have 30 different instruments. Okay, so we have roughly 30 different instruments. The nice thing about building these guide halls is we can pump the neutrons out, very similar to the way fiber optics works, but we have a similar technique for neutrons called neutron guides. You bring them out and build a whole new suite of instruments. Costs you the same amount to run the reactor, but you get all these neutrons basically for free, other than you have to pay for the instruments and people. Okay. Different spectrometers. How come we have all these different spectrometers? They cover different angular ranges, and I'll show you back in the next part of the talk various examples of how we can use these. For structure work, we can go from centimeter scale, where you're doing actually imaging of items, down to the angstrom. So basically, 8 or 10 orders of magnitude in size. For inelastic scattering, we can basically go about 7 orders of magnitude in energy, 7 orders of magnitude in length scale. And each instrument has a, so if you're interested in excitations in iron superconductors that go up to 200 milli-electron volts, you need a certain type of instrument. If you're interested in a protein that folds or unfolds, something like that, that's a very large object. It's very slow. You need much better energy resolution. And same thing for hard matter. Okay. So in summary, crystallography, you do powder diffraction, single crystal, you can get atomic positions, site occupancies, lattice parameters, bond distances, mean square displacements, and you can do those all as a function of temperature, magnetic field, pressure, whatever thermodynamic entity you're interested in. And you get the same type of information for magnetism. You get magnetic structures, order parameters, a function of temperature, for example, spin directions, phase transitions, critical phenomena. The small angle scattering, we say everything is inverted in reciprocal space, so things that are big in real space scatter at small angles. And the kinds of things that we'd be interested in is ferromagnetic correlations, vortex structures, domains, defects, nanoparticles, skyrmions. Those are the things you're going to use small angle scattering for. And then thin film reflectometry to look at thin films and multi-layers. You get a density profile and also a magnetic profile. It's a magnetic system. Okay, inelastic scattering, lattice dynamics, basically, and spin dynamics, magnon dispersions, things like that, crystal field levels, various kinds of excitations. So here's a number of research participants. Back here in the Stone Age, there weren't a lot of people that came through. Then we got the first guide hall, and then we got the second guide hall, then we got COVID, and then we shut down. And right now we're shut down, and we expect to be back up in operation by the summer. So this is tailing off. Two other facilities, very useful, a high flux isotope reactor at Oak Ridge National Lab and spallation neutron source also at Oak Ridge National Lab. One's time of flight, it's a pulse sources, and one is a steady state. And in all these facilities, and also the ones overseas, you basically have a call for beam time proposals about twice a year. You put your proposal in, you hope to get some beam time, and you go in and do your experiment. Okay, thin films and multi-layers. So the idea here is you come in with a polarized beam, and it scatters. We affectionately call this mirror scattering. So it scatters, and then as you change the angle, beam penetrates in. You Fourier transform that, and you get a depth profile out of that. So that, and here's one example. You can actually do this to measure the London penetration depth in superconductors, but that's actually very difficult. I've done it for niobium. It's a difficult experiment. It's not done very often. Much more often is either biological systems in polymers and magnetic systems. Okay, so this is an example, very difficult material, but the idea is this is a multiferroic. Somebody mentioned multiferroics, they like them, and I like them too. And so this is an example where you're taking an electric field and trying to change the magnetism. That's the one of the things. And so what you see here are two different curves. They're almost identical. This is a very small effect. And here's the actual material. It's calcium manganese oxide, calcium ruthenium oxide. And this is for a single layer. And that, for neutron scattering, typically it's a system that's flux limited. So doing really small samples is very difficult. And at the end, I'll tell you all about what kind of samples you actually need. But in fact, you can see a difference by applying a voltage versus no voltage in the system. So you can actually train the magnetism and control it with an electric field in this multiferroic. Okay, materials that are both magnetic and superconducting. So I've been doing this for a long time, and we've already mentioned that if you want to apply a magnetic field, typically that's not a good thing to do on a superconductor. You can certainly extinguish it. So you apply a field and you go into the normal state. So basically, superconductors don't like magnetic fields. And even worse, you have a Cooper pair here in the conventional theory. One spin up, one spin down. And the worst thing you can do is to put magnetic impurities in that break up those pairs. And so this is TC versus concentration. And almost all materials follow that curve there. That's the theory curve by Abrakrosov and Gorkov. And it dives down to zero at a specific critical concentration. And typically that's like 1–2%. So a couple percent, you're never going to get any collective magnetic behavior in there. So in magnetic superconductors, you don't want to put anything in this magnetic in there. And then there's the exception to the rule. So anytime you're doing research and you have understanding and a paradigm of how things are supposed to work, and suddenly you find a system that doesn't behave, that's when you're on the new physics. And the first new physics was back in the 60s. Believe it or not, that was before my time. And, but these cubic Lattice phase, you could put heavy rare earths and all the heavy rare earths and up to 10, 20, 30% before you really affected the superconductivity. So that was a big surprise. And then shortly after that, materials were discovered which have a whole periodic lattice of magnetic atoms, and they order antiferromagnetically. Almost all of them order antiferromagnetically and coexist with superconductivity. So that was the exciting thing back in the 70s. And then even more exciting was there were a couple of systems where they ordered ferromagnetically. And when they order ferromagnetically, there's a macroscopic magnetization, and that's got to compete with the Meissner effect. So you see a very strong competition between that. And then along came high TC cuprates, 1986 they were discovered. And so those are, we've already seen some of those like yttrium, barium, copper oxide. And then the boron carbides came after that. It's too bad. The boron carbides, beautiful systems, but they're not high TC like the cuprates. But they're very interesting. Then there were some that were ferromagnetic superconductors, and many of these were either not magnetic at all or antiferromagnetic. But some of them actually in the uranium materials are ferromagnets. And then the sodium cobaltates, and we heard a talk from Ephraim about that. And you take these systems and you add water, and the C-axis almost doubles, which is incredible. You can take a single crystal, put water in it, it doubles the C-axis, maintains a single crystal, and a superconductor. Unfortunately, it's a lot, we call this instant superconductors. It's like instant coffee. Yeah, it's a superconductor, but not that good of one. And then, of course, iron-based superconductor. I'm not going to talk anything about hydrogen materials because there's been hydrogen materials that are superconducting under very high pressures because neutron scattering can't do that. Okay. So I thought we should, nobody's explained yet what a ferromagnet is. So I thought I'd better put that in. JP insisted that we keep this pedological. Anyway, so there's a spin. You bring a second spin in, it's got to be parallel to the first. And the third spin's got to be parallel, and parallel, and parallel, and parallel. Okay, so there's a ferromagnet. I'll bet you nobody's ever seen a ferromagnet like that. You look in the textbooks, they're always up. But down is just as good as up. Right? That's, or any other angle, as long as the spins are parallel. That's a ferromagnet. Okay. Antiferromagnets just up, down, up, down, up, down. And then spin density wave, typically you have a variation that looks like a sine wave. Typically that sine wave is incommensurate, which means it doesn't line up with the lattice. It doesn't necessarily have to be that way, but typically that's what we call when it's incommensurate. Okay, so one example, and these examples I'm just pulling out, A, for my convenience, because I was involved in the work, so I have the slides, and B, it just demonstrates the different techniques that you can do. And so holmium sulfide was one of these Chauvel phase ferromagnetic superconductors. It goes superconducting at 1.8 Kelvin, and ferromagnetic at about 0.7. And the ferromagnetism, holmium's a ginormous magnetic moment. It produces a large magnetic field, quenches the superconductivity. Holmium selenide is 5.6 Kelvin, so TC is higher, and the ferromagnetism is lower, so it's the competition is such that it doesn't re-enter normal state, it remains superconducting all the way down into the ground state. So these are ferromagnetic materials. How do we actually study them? Two different ways. One is to do the diffraction pattern to see if it looks like a ferromagnet. And this is the simplest type of ferromagnet you'll ever see. You see the Bragg peaks like here, 100, 110. I just index them according to a cubic. This is our rhombohedral, but you can't tell the difference here. And there are a couple things that notice about that. First, there's a sum rule on the scattering. So the sum rule is that if it's just a spin, it's S on the S plus 1. And you expand that out as S squared plus S. And where do those two terms go? Well, in the paramagnetic state, you have no, assuming you have no correlations, that scattering is just spread out. It's just background, okay, in this slide. And then when it orders magnetically, that S squared goes into the Bragg peaks. Okay, so, and then you have a deficit of scattering everywhere else. So there's, because the scattering has shifted from everywhere up to there. Okay, so when you make a measurement, you make a measurement of the square of the ordered magnetic moment in the system. The other S part here, that's all the inelastic scattering that's left. Okay, so Bragg peaks, as I mentioned at the beginning, those are delta functions. Delta functions are really easy to see. It's a delta function in Qx, delta function in Qy, delta function in Qz, and a delta function in E. So you know right where that guy is. Inelastic scattering is spread out in Qx, Qy, and Qz, and energy. So if you're lucky, it's actually the dispersion surface, not like a spin liquid that's everywhere. And so that's why the size of the samples are very different, whether you want to do single crystal diffraction versus inelastic scattering. And I'll show you some examples as we get going here. Okay? Now, the other thing I wanted to mention is you see this upturn in scattering down around 0. 0, 0, 0 is always a Bragg peak. The only problem is that's where the main beam is. So you'd like to know what that scattering is, and the way to look at a ferromagnet is to do small angle scattering. So you bring a monochromatic beam in, put your sample, and you have a two-dimensional position-sensitive detector. Right in the middle is a beam stop, so you don't damage your detector. So that's the kind of hole in there. And what does the scattering look like for homeimide sulfide? So if you look very carefully here, you'll see there's a little bit of a ring of scattering. This is at 0.72 degrees. It orders just at like 0.73. And you cool down a little bit more and you see a nice ring of scatter. This is a powder, and that's the powder ring that you would measure if you do X-ray or neutron diffraction to do crystallography. I showed you how those rings look like. You can actually measure the whole ring. And then when you cool down, it goes up in intensity, and then it kind of collapses into ferromagnetic domains. So here's what the intensity of that ring looks like. As you cool down, comes up, and crashes down here, and very hysteretic on warming and cooling. And here are the TCs that you get in there. So it's a strongly first order phase transition when the ferromagnetism quenches the superconductivity. Now here's a better example, more equitable system, and you see this ring of scattering. If you look carefully, you see this ring looks bigger than these other rings, and that's correct. The previous one has a length scale of 200 angstroms, 20 nanometers. So this one is about 100 because the superconductivity is stronger. And it, all the way down to T equals 0, it forces the ferromagnetism to be truncated in the system. So this is what the scattering looks like. If you look at that, you see that these peaks grow and they're moving into Q equals 0. Q equals 0 is where it would like to be ferromagnet, but it never makes it. And so you see, top one is the intensity, the bottom one is the wave vector as a function of temperature, and the solid line is a theory that Richard Farrell, who's here at the University of Maryland, conjured up for this. Another type of example is this erbium nickel boron carbide. It has a TC of 11 Kelvin, and it goes anti-ferromagnetic at 6 Kelvin. And then Paul Canfield and collaborators found another transition down at 2.3 Kelvin. And you look at the red curve here at 4.6, you get nice incommensurate magnetic peaks. So this is at roughly 0.55 Q. So it's not 0.5, it's not 1, it's not a quarter, it's some incommensurate value. When you start cooling down, you go from a sine wave here into something that starts to square up, and you get additional peaks. And then when you go down below 2.3 Kelvin, you still get a whole new set of peaks in here. And what happens is the system wants to try to latch into the lattice, but the incommensurate peak doesn't fit there. So every once in a while, you'll see there's an error where two spins become parallel. That gives you a net magnetization in the system. So we should be able to see that in the vortex lattice. So how do you do the vortex lattice? Well, you do vortex lattice by small angle neutron scattering, because the lattice parameter for the lattice is large. Things that are large scatter at small angles. And so here's the vortex lattice. And then when you go down into the lower transition, it spontaneously produces more vortices in the system. You put more vortices in, the lattice parameter of the vortex lattice gets smaller. That means the peak should shift out to larger wave vectors, and that's exactly what you see. Okay. And crystal for this was about 1 millimeter by 1 millimeter by 3 millimeters for this, just to give you an idea. Here's another vortex.
Sorry, why does the peak shift? So you went through this magnetic state, there's more vortices.
When you shove more vortices in, so that means that the lattice parameter has to get smaller to accommodate that.
So vortex lattice.
Of the vortex lattice, right. And if the lattice gets smaller, then Bragg peaks are going to shift to larger Q. It's just inverted. Here's another example for niobium, and this is with Sean Ling at Brown University. And the interesting thing is that when you got up close to the upper critical field, you actually get a vortex liquid in the system. You get a powder diffraction, whereas at lower fields, you get a nice vortex lattice. So that's kind of and I think somebody mentioned about vortex liquids. Yep.
Is that temperature dependent in niobium?
Sure. Yes.
You can't see this at very low temperature.
Yes, you can see it at low temperature, but you have to go up to higher field. Yeah, this temperature should be on here somewhere. But basically, the interesting thing is to look at this peak effect. So it's a lot easier to see up at high temperatures, close to the phase transition. Iron-based unconventional superconductors. So this is what we affectionately call 1111. It's a tetragonal system. And you have the copper ions, and it actually on a square lattice. If you have to cock your head about 45 degrees. And that's the crystal structure. And the basic properties, parent materials are metallic and also long-range ordered. They're anisotropic, but not nearly so like the cuprates. And there's a structural distortion. So you start tetragonal, and then as you cool down, most of them have a tetrahedral orthorhombic distortion. And then the iron spins order antiferromagnetically, and that phase transition can occur at the structural transition or below it. And there are examples for both. TC is pretty high, 56 Kelvin, claims up to 100 Kelvin. I don't think anybody believes those anymore. Maybe. Anisotropic, very high upper critical fields. And here are some of the examples. And I think we've already gone through those, but people got tired of just talking about them, so they just gave them numbers. So if there's iron, selenium, it's 1,1. Lithium iron oxide, 1,1,1, 1,1,1,1, 1,2,2. You get the idea. Many different materials. Here's a powder diffraction system, and I mentioned that it structurally distorts, and you can actually see that. So this is a blow up of that peak there, and you see that as you go down to lower temperatures, it distorts, goes from tetragonal to orthorhombic. That's really kind of important. And here's the first magnetic scattering, and you can see the magnetic scattering very easily here. See those big peaks? No, that's not it. There's a magnetic peak. Yeah. So these are spin-and-a-half systems, less than a Bohr magneton. I mentioned that the scattering goes like the square of the moment. So if you look at holmium and you got 10 Bohr magnetons versus half a Bohr magneton here, you're missing a few orders of magnitude. But you can see these. So if you blow those up, you see these peaks. There are 3 of them here, maybe, and there are a couple more actually under those big peaks. Enough to solve the structure and to measure the order parameter. These are the first measurements of that. If you're lucky enough to do the first measurements in any system, then you get a lot of citations. Now that's for a powder. You can do much, much better with single crystal. Once you know the basics, then here's a single crystal. Here's a particular peak cooling down as a function of temperature. And you see it splits. Here's the actual intensity. So here's the intensity on the top of the peak, and you see, boom, it just drops down. That's the red curve. And then for this particular system, which is strontium, iron 2, arsenic 2, the long-range antiferromagnetic order comes in at the same temperature as the structural transition. So the system, when it's tetragonal, is fully frustrated and doesn't order. Typically, as soon as you break that, make it orthorhombic, then it can order. Okay. And then in addition, we were able to do inelastic scattering, the very first measurements of inelastic scattering. Very difficult to do. We had a really small sample. This is the same material. And you see here at the top is energy versus Q. You have these antiferromagnetic spin waves. You can take that and model it and realize that those excitations should go up to like 200 millielectron volts. 200 millielectron volts corresponds to 2,000 degrees in temperature for thermal energy, KT. So these excitations are order of magnitude more than any phonons in the system, order of magnitude bigger than what you would anticipate from the ordering temperature. And that's why the first indications that the pairing mechanism must have something to do with the magnetism rather than phonons. Okay. And then we've had some beautiful lectures on the order parameter for the superconductivity, D wave, and a D wave will give you a special spin resonance in the excitation spectrum. And that proves that the system is unconventional. Iron superconductor is the same idea. So this is energy, and you see this new excitation come in. The intensity of that just follows the PCS type order parameter, pairing order parameter. That's a magnetic excitation in the system. So you know that this is tied directly to the pairing in the system. And all the unconventional superconductors, including the heavy fermions, show this type of exciton in the excitation spectrum. Yep.
How do you know if excitation is from S pairs?
Oh, well, yeah, that's a good question. Just looking at it, you don't know. But you do know that there has to be a sign change of the pairing on the Fermi surface, whether it's plus minus or D wave, which is going around 90 degrees. This data won't show it. What you need to look at is, first of all, you need to know where this occurs in reciprocal space. It only occurs at one place. That can be a hint, but it doesn't prove it. Okay. This was 5 coralline single crystals. And so this is, you know, much easier experiment, and it was all already a year later. So, you know, things were moving pretty fast. 10 grams, and typically it's difficult to grow 10-gram single crystals. You can do it, depends on the material. But one thing you can do, if you want to get the size of the sample up, you can co-align crystals. So this is 5. 5's kind of a nice number. How much time have I got? A couple minutes. Half Hoistlers, so JP, I had to put this in. JP insisted. Yeah. Put your wallet down, JP. Anyway, these are really interesting systems. They're cubic, and the magnetic ordering wave vector is anti-ferromagnetic, and we've done a whole series of the different heavy rare earths in this system. So here's the co-conspirators. Shanta is probably somewhere in the audience, maybe, and JP. And the interesting thing is that they're non-centrosymmetric, so that means that you can mix, you know, odd and even parities and this thing. FCC lattice turns out to be fully frustrated type lattice, low carrier density, and then there's long-range order and unconventional superconductivity. And these materials are also topological, so you got everything. And I mentioned topological, so as you go across the rare earth series, you get a band inversion right around half, and you go from topologically trivial in the upper part into topologically interesting in the bottom part. I'm not going to go into that, but for the neutron scattering, we do single crystal diffraction to get the magnetic order parameter. Here's a nice diffraction pattern, just scanning along one particular direction. And in this single crystal, you get the order parameter out, and of course you get the structure and the spin directions. And then the interesting thing about this is that as you get a bigger and bigger spin, then it should scale according to the gen scaling, and that's exactly what you see in this system. Okay. And then the final couple of minutes, yeah, I got the, looks like it's, talk about one brand new system, and it's interesting because here's the formula here, and it's kind of an interesting material. This is a guy who made it. He's still alive. But, you know, I'm a physicist, so chemistry is dangerous. And this chemistry is, yeah, so they do it, I think they put it under pressure with the copper and silver. I think they put the oxides in sulfuric acid, right? Which doesn't sound good to me. Although I've had my acid training. And then once you get the material, then you wash it with hydrofluoric acid. And I was very happy to find out that these samples were made in Europe and ice saved and then shipped to us. Okay. And the interesting thing, this is really a beautiful paper here. This paper, I really recommend it. They did a beautiful job. They did DFT calculations, to find out what the magnetic ground state might be. And the most interesting thing that maybe you haven't picked up yet, it's got copper and silver. Copper is spin a half. How many people have worked on silver materials that are magnetic? I guess I'm the only one with my hand up. It turns out that silver also spin a half. At least it's predicted to be. Okay, so we want to do the neutron scattering. And Igor here is the guy who is a theorist. And that, you can tell that he's the theorist because look at the size of his head. But he realized that the predicted ground state should be an alter magnet. And so we wanted to do the diffraction. And so it orders around 40 Kelvin. There's a susceptibility. And then the two magnetic structures that these guys, and this is really the good paper as well, is the lowest energy. This one should be an alter magnet. And so Igor and colleagues looked at that. Double cell is the next lowest energy magnetic structure. And when we did the diffraction, we could rule that out immediately. So here's the band structure from Igor's paper, and you see from the gamma to R, this is a monoclinic material. The bands are spin split. That makes it an alter magnet. And then we did the diffraction at Oak Ridge with Daniel Yanni. And here's the subtraction technique. So I subtracted off the nuclear scattering, and you get two peaks here. You can see them. Now, anytime you get peaks and the statistics aren't as good as you'd like, you know, put a smooth curve through them. It looks much better. And you get these two peaks here. So that's, and we can measure the temperature dependence to say, yeah, that's magnetic. It orders around the 36, 37 Kelvin. And then the question is, can you understand the magnetic structure? So you can say, well, you know, I don't really believe the silver's ordered magnetically. Maybe it's just the copper. So here is a list, and if you look at the 2 theta list here, you see, well, there should be a big peak at 10 degrees, and there's nothing there. Okay. If it's just the copper, the 12 and a half, that is there. But then there are all these other peaks that should be there and aren't there. Okay. So then what you can do is to use the alter magnetic structure where copper and silver both have a magnetic moment, and you can explain the pattern completely. Okay. So this we believe is an alter magnet. And we're anxious to get this written up and published. We'll see.
Hey, Jeffrey, are the crystals, I mean, the peaks really weak because silver has like a really weak form factor, you see?
Yes, that's one reason. They're both spin a half, and it's a pretty small sample. Yeah, so, and a powder. And it looks like there's a little bit of hydrogen. I mentioned that hydrogen is the Guinness World Record cross-section for nuclear scattering. If you leave any hydrogen in your sample, you'll get extra background. So that gave us something. Now I mentioned at the end about what size samples do you need. And if you're doing thin films, typically I showed you one example with a single layer of material. It's really very tiny material. Thin films typically are also, because you have a huge substrate, typically, those always challenging. The reflectometry experiment, that's fine. If you want to do, for example, magnetic diffraction, that's really a challenge. Diffraction, typically you'd like single crystals and the milligram size. You don't want them actually too big. If you go over like 100 milligrams, typically you're starting to get extinction effects and things like that. It gets more difficult to interpret things. Powder, you typically, if you're doing powder diffraction, it's nice to have like a gram size sample. Dynamics, you like gram size samples. And that's because the scattering is just spread out in reciprocal space. The smallest one I've ever done, where I got actually inelastic scattering, was 2 milligrams. It was on a magnetic system with a dysprosium with a ginormous magnetic moment. That's very unusual. Biggest is, and usually when I ask people for single crystals, I ask them how many kilograms is your crystal. And that's 0.4 kilograms is the biggest one I've ever worked on. And then you can co-align crystals. I showed you one where you got 10-gram single crystal, and those actually grew rather nicely. The most crystals I've ever co-aligned, and I didn't do it, is 1,115 crystals. This was for a spin liquid system, and the graduate student who's doing that now very well is Rebecca Smaha, and when we wrote up the paper, and I hadn't asked how many crystals there were because they were all sealed up, it's air sensitive. And I said, are you sure it's 1,115? I think maybe one of the crystals fell off. And she responded and says, well, next time I'm at the NCNR, I'll count them again. Yeah. So if you're going to do that kind of crystal alignment, you've got to have nice edges. Typically, if they grow flat, you can get one axis for sure. If they have nice edges, then you just kind of put a mosaic together. It wasn't like you got crystals that you had to orient them with a beam in 3 dimensions and get the different crystals aligned up, which is what they had to do with the iron and selenium that I showed before. Okay, the overall summary, I talk about neutron scattering, diffraction, and dynamics. I tried to give you some examples of magnetic and electronic and lattice experiments for superconductors, magnetic phase transitions and order parameters, structural phase transitions, the exciton resonance in unconventional superconductors, vortex lattice, that's a really nice, and alter magnets with possible superconductivity. This is a cuprid, so the next question is, can you make that copper-silver material superconducting? Hasn't been done, and I'm not going to make any samples of that. I'll let the chemists in Europe do that, or Ephraim. And I'll just give you some references, so it'll be on the web when they put the recordings up. Anyway, well, so thank you very much for your time. Any questions?
Are you able to differentiate between peaks that are due to this crystal structure versus magnetic structure?
Yes. Yeah, so one way you can do that is just to look at the temperature dependence, for example. And that subtraction technique does that very nicely. Okay? But it doesn't prove that it's magnetic. But you can use polarized neutrons if you need to prove that it's magnetic. Okay, so typically what happens is for most materials, the electron scattering and the magnetic scattering, the intensities are just additive. So I showed you holmium bisulfide. The ferromagnetic peaks sit right on top of nuclear peaks, but you can subtract that out. That works as long as you don't have to go through too big a temperature range, where you get the Bi-Waller effects and things like that, and no structural distortions or strong magnetoelastic coupling. But if you need to, you can do polarized neutrons and then unambiguously and uniquely tell. And you can also do that for order parameters. There was a question about order parameters. You can look at the exciton resonance, and we've done that with polarized neutrons to get the symmetries out. Excellent question.
Yes.
Anxious to get.
Let's thank Jeff again. Yeah. Good moment, Jeff.
Okay, last day of the tractor.
Oh. Yeah. Oh. Yeah. I'd have to go back and look. That's a long time. You know, that was during the previous millennium. So I don't remember. I mean, it's much. Yeah, that's right. So you just. I think it's in the supplemental material, but I didn't redraw that. Really, I doubt that they're ever going to be able to go single crystals with this, but there's a similar system that, it's all powered. Hi. Uh-huh. Say it again.
If you want to do the nutrient CD crystal,
Yeah.
and if you do the powder, that's exact CD crystal and do the powder difference. Is there any difference in that?
Well, typically, for single crystal, you get much higher quality data.
They want a second.
So the nice thing about doing the powder at first is you don't miss anything. You go with single crystal and you say, well, where do you want to look? Right? If you don't look in the right place, you may miss something really important. Right? So it's nice to do the powder diffraction first, then you can go to the single crystal and get much more. And typically, powders are going to be available first. Oh, it depends. So that it depends on the details of what you're looking for. If you're looking at magnetic scattering, for example, magnetic scattering can change by 2 orders of magnitude strength, the size of the moment. Bright peak scattering goes like the square of the moment. So from 1 Bohr magneton,
Or are you uniting?
up to 10 Bohr magnetons. Factor of 100. And neutron scattering is flux limited. We wish we had, the intensity. Every neutron scatterer wants higher intensity and better resolution. Right? And they're always in conflict.
It's far too, and they wanted it 25.
No, not necessarily. Antiferromagnets, usually antiferromagnets are easy. Because often the bright peaks, magnetic bright peaks are physically separated. Doesn't have to be there.
You're back. I know.
So if they're separated, then it's much easier. When I showed the homing sulfide, the structural peaks and the magnetic peaks are right on top of it. But for the homium, which I did back in 19.
I remember my house had it once. Everybody, no, I don't know what it is. It's a 2-factor.
Well, yeah. Well, actually, I'm officially retired in June, so this is just a celebration, just a party.
You can really get away with it.
Well, I have a lot of papers, so I don't have to do all the BS paperwork and performance plans and training. I don't miss that at all, so, and I can just do my research. No.
As a beginner.
No. And by the way, for beginners, want to do an experiment, contact either Oak Ridge or us, contact the instrument scientists. They're happy to help you out.
I actually went through those patterns.
We can get 10 people then.
Okay, yep. I did my thesis at Oak Ridge.
It takes a year.
Yeah. Well, yeah, so it's a thermal triple X.
Is that what it said? I thought they were just
So,
sitting on a fire. I thought that was a joke.
That's what something about the rest of the
my most recent postdoc is Eleanor Clemens.
Yeah, I should ask them what it is.
On the thermal triple axis.
Yeah, I just wanted to see
Some space, and that's about it. We are everything else.
that's okay.
Yeah, I was just going to try to. Where's the cursor? Oh, there it is. Okay.
Oh, like I really green trioxide, which is a beautiful powder red. It looks like
Here's this guy.
like before it.
Oh, here.
I got this anyways.
We got everything now. I'm talking about green metallic. But never purple. They wanted to see how.
But that was like.
Yeah, sorry.
Oh, no, that's good.
Yeah.
I would love to transfer it on.
I will be there.
I think I need to ask you a probing question because I have to go through practice.
You're all right. Where are you from?
I'm today. Yeah, I'm sure. So, sorry.
I'm going to tell them that they leverage.
Yeah, this are. Yeah.
You're right.
So I was wondering, first, I sure you're
Second way.
Just one
Okay.
Typically, you already know, before you ever put it on spectrometer, you measure the minor effect.
That's the last.
Traditionally, you always want to
Some ways.
in fact, you won't get meaningless more.
Unless you have
Proposals are short.
Actually, yes.
Proposal is scientific review and also usability. First thing, look at so you should already know. Which one do you like?
I am not sure to be honest. I was thinking my second question talk about
So we're just saying.
I don't think that's it.
Even your eyes.
So that's what I'm saying. So if you were there,
Yeah, I saw you. We have about 30 happy to share that I'm only I hate that
Well, typically, you use a substrate.
happy to share.
That story is for magnetic.
Yeah, what else was we'll definitely do more. Your rate is also from QMC.
Oh, so they know the reference line.
So spin it.
Thank you so much.
I think it's not sure if it's as simple as that. Originally by Frederick.
I know.
Very new area for me, but I'm very grateful.
Oh, yeah.
I think I was thank you so much. It's a pleasure. I think we're awesome. It's all about workshop.
I don't have their.
I was just going to go over here and see if I found shit.
I'm so sorry.
What did you do? Do you remember which one you did last? So you should be in philosophy. It's a philosophy. If you're wondering why
Don't tell them. It should be that. Oh! It's not like that. It's like I wonder how many people are Yeah, you have to really, yeah,